Our next speaker is Mark Blanton, who will be giving us an Artemis architecture overview.
All right, thank you for the introduction. Can you hear me just fine?
I can. Sounds great.
Awesome. Let's go to the next slide. So as part of the mission analysis and integrated assessment team, we have to take a look at a variety of the different architectural elements as they are developed and designed and then executed in order to put together a mission that satisfies the objectives, not only of the mission that we're currently working on, but pave the way for future missions. And so I specifically took the following 6 elements to talk to you today, given the context of the meeting that we're having, because I want to try to emphasize some of the constraints that we're working with as we design the missions. And then what I'll do on the next couple slides is I'll show you the Artemis 2 mission, what you'll see in terms of the trajectories that we're flying, the view from the spacecraft that you might anticipate seeing, as well as the Artemis 3 mission, which when you see the trajectory, you'll be able to see how different elements within here could be extrapolated to those future missions that folks were talking about earlier in the presentation. So everything begins here with EGS, and it's the pre-launch and launch operations that allows us to understand when we can actually launch the vehicle, get the hardware, and then if we have problems at the pad, like we did for Artemis 1, how we recycle and how we maximize the number of launch opportunities to make these missions happen. So we're really going to use all of the knobs that we can in order to get a mission off the ground, and that also includes the landing aspect of the mission, which is, recovering the Orion crew capsule with the crew in the San Diego area. And what folks might not be aware of, but we're a little bit different than Apollo, where we don't have a whole lot of Earth surface area that we can cover with our recovery crews. And so one of the factors that we have to include as well is the recovery area near San Diego. Another second big element of the mission is, of course, the SLS rocket. And, it's providing our first stage and second stage boost, as well as the in-space propulsion that's going to send the Orion capsule to the moon. And so combining that with the Orion spacecraft, we are looking at how can we blend these 2 elements' capabilities to take 4 crew out to the moon with the propulsion capabilities and the consumable capabilities, not only of the upper stage and the first stage, but as well as what can the Orion spacecraft contribute to the trajectory and the mission feasibility. So we take those first 3 elements, and specifically for the Artemis 2 mission, and we begin to maximize opportunities performance-wise to get this mission off the ground. Now, for the Artemis 3 mission, today we have one, we're using SpaceX for Artemis 3, and it's been talked about. Artemis 5 will use the Blue Origin vehicle. They're 2 different contractors, obviously, but they each are building designs that enable us to get to the South Pole. And we'll be meeting them, I say we, the Orion spacecraft and the crew will be meeting these vehicles in the near rectilinear halo orbit, or the NRHO, in order to then go down to the surface, whether that's via gateway or direct docking. And of course, in the NRHO, the crew will be descending to the lunar surface, and you folks have probably talked about these in other meetings, but the surface day is roughly around 7 days. And so the NRHO mission, of course, follows sort of that rhythm as well. The last architectural item I want to talk about just briefly here is the Gateway, which is a multi-element spaceship that will be in the NRHO and serves as our aggregation point for the crew, supplies, and the lander vehicles on the later missions. Gateway also supports a number of scientific research opportunities from the NRHO. So with that, let's go ahead and take a look at some of the pictures and the video that I have going here. Of course, everyone's going to be looking at the videos on the right while I'm talking and probably won't, hear a lot of what I'm saying. But we'll talk about the image on the bottom left for just a second. So in order to maximize the number of launch opportunities and the performance capabilities of Orion getting to the moon, we have to insert into a highly elliptical orbit on the first and second stage. That allows us to get enough energy to then, for the Artemis 2 mission specifically, to go into a very highly elliptical orbit. We're using that first large orbit there you can see in order to test out the crew systems, carbon dioxide removal system, and another other things that the crew will be using for the first time before we commit to going to the moon, which happens after about 24 hours in this orbit. And like was said, it's about 4-day transit out and 4-day transit back. So what you're seeing here on the trajectory and the view of the moon piece here, hopefully they're synced up pretty well, is the flyby that will be performed that you can see on the bottom left-hand side. Of course, what I'll say is the mileage may vary depending upon the launch day that we go on. But what we're seeing as a time of closest approach are a range to the lunar surface of roughly 5,400 kilometers, all the way out to 13,000 kilometers. The one you're seeing here in the image is roughly about 8,700 kilometers. And so the image also shows roughly about a day before the TCA to about a day after. And that roughly gives you an idea of what this trajectory will look like. And to kind of pile on what was said earlier about knowing what the trajectories are going to look like, we'll have good sets of data here as we begin developing the actual products for the Artemis 2 mission at the beginning of the next quarter of 24 for an intended launch date of December-ish 2024. So we'll have all the insight that we need in terms of what these trajectories will look like, what the lighting environment will look like for that mission. So with the balance of the time, and I love the clock, by the way, let's go to the next slide and talk a little bit about Artemis 3. So we're using a very similar insertion trajectory that we saw for Artemis 2 into Earth orbit. We're not going to be doing a highly elliptical orbit on the second rev because we've already demonstrated the crew systems on Artemis 2. So following the first rev at perigee, we'll do TLI, and we'll head out to the moon. Now, depending upon the day we launch, could generate trajectories that take the crew out from anywhere 4 days all the way out to 11 or 12-ish days to get to the NRHO, where they will insert. And you can see that in the top right-hand corner of that image at the bottom left, and they'll meet up with SpaceX Starship, in which case they will spend a few days in the NRHO together while the crew transfers, gets ready to enable their spacesuits and perform the lunar mission, at which point they will descend to the low lunar orbit. That takes roughly half a day to do. They'll spend a couple orbits potentially in low lunar orbit to get their guidance and navigation and trajectory all updated for the approach to the lunar surface, and then they'll descend. And after they're spending time at the lunar surface for 6.5 days, they will do the opposite. They'll ascend, spend a couple of revs, and then depart for the NRHO, where they'll link up with Orion, and then return to Earth. And so what you're seeing here for outbound trajectories is a roughly 100-kilometer approach for the outbound power flybys of the moon. And then when we return, coming back to Earth, it's roughly the same at 100 kilometers. The TCA that we're seeing, or the altitude that we're seeing at the time of closest approach from the NRHO, has been in the range of around 3,300 kilometers. And at the farthest point in this orbit, we're seeing roughly 70,000, 71,000 kilometers at the farthest point. What you're seeing in this video is a fairly low pass, and that's dependent upon the NRHO. This one's approximately 1,600 kilometers. And yeah, you're getting to see a real differentiation, a dramatic view of the moon, depending on where you're at in the orbit, whether you're at the highest point or the lowest point in the speed by which we pass over. So hopefully this gives everyone a sense of the trajectories that we're flying for these two missions, and then gives you a representative of what the NRHO will provide those vehicles. That's all I have for today.